Okay, we're looking at Calculus 1, Section 4.6, the mean value theorem. So the mean value theorem first starts off with Rawls Theorem. Okay, so Rolle is one of the less celebrated mathematicians whose name is nevertheless attached to a theorem. He worked in Paris once again in 1691 is when he started developing this. So in Rawls Theorem, we take a look at that if f is continuous on a closed interval of a to b and then is differentiable from a to b. So once again, the main purpose of this is we have to have an interval and we have to be differentiable on this interval continuously. If any point is not differentiable in here, Rawls Theorem does not apply to this. Okay. Basically what we start looking at that if our endpoints are the same, if f of a equals f of b, that means there is at least one point in between here where the derivative of that value is going to equal 0. So if I come over to the graph that's in right here, if we look at this, notice that we have this graph. So here's our overall graph going on where we're on interval a to b. We're differentiable everywhere on this graph. So we have a nice continuous graph that is differentiable everywhere. We see that our endpoints hold the same value of our y right here. So f of a equals f of b. One point in the middle here on c is going to be 0. Once again, we are going to have some sort of local maximum or local minimum. Basically is what this is starting to relate to. So then on the next pages, they have a couple proofs that kind of go with it. So if you want to look through those proofs, they kind of show you on why this goes. Now our mean value theorem. Okay, so our mean value theorem is an important theorem in calculus. It basically kind of talks about the fact that we have at least one point in here. Okay, so we talk about if f is continuous on a closed interval of a to b and is differentiable on the open interval a to b. So that means we have a continuous graph. Then there is at least one point c in AB such that f of b minus f of a equals b minus a, which equals the derivative of c. Okay, so what we talk about here is not necessarily having an overall 0. We're talking about that if we have a and b right here, and we look at the slope going through these 2 points, there is at least one point somewhere on this graph that's going to share the same slope as what this is. Now, what this is really starting to relate back to is, remember back when we started first talking about derivatives, and we started talking about tangent lines and secant lines. This would be that secant line that we have those 2 points that we're going through here, and then as those points get closer and closer, they have that tangent that go right here. Now, granted, we did the secant line, we brought this point back to this one. Here we're talking about taking these 2 points and going back till we share a same slope. Okay, so that's what this mean value theorem is starting to talk about. Basically, what it really relates to is as we consider this, we start considering like story problems where we could have this wavy graph going in. We looked at overall here, but we could look at the mean value theorem guarantees that there is at least one other point in here that has that same temperature change that would be going on throughout here, so we could look at that instantaneous. Now some other formulas that were spin-offs and work with this is that zero derivative implies constant function. Okay, so if f is differentiable and f prime of x equals 0, all the points on the interval I, then f is a constant function on I. So basically they're kind of going through this whole proof right here that states that if we take the derivative and the derivative equals 0, that means our original function was a constant. Okay, we just had a constant function going into this. We talk about functions with equal derivatives differ by a constant. So if two functions have the property that f prime of x equals g prime of x, and x for all x on an interval I, then f of x minus g of x equals c on I, where c is a constant. That is, f and g differ by a constant. Okay, so if we see that our derivatives become the same, then we know that our original functions might just have a constant difference within there. For instance, if they both were linear, we could have a different y-intercept on there. What this is really getting importance to is kind of leading up towards our Euclidean parallel lines that we kind of starts relating in there. And then we talk about intervals of increase and decrease. Let's straighten this out a little bit here for you. It says, suppose f is continuous on an interval I and differentiable on all interior points of I. If f prime of x is greater than 0 at all interior points of I, then f is increasing on that interval, and f prime of x is less than 0, then we're decreasing. So once again, this is kind of relating back to our slope of our line. Once again, we could talk about increasing, decreasing functions. We did this back in section 4.3, 4.2 in there, when we talk about increasing, decreasing. Basically kind of relating back into that slope of what's going on within here and everything that is related. So this is section 4.6. One of the main things that we really do in here, we'll do a little bit with Rawls Theorem, but that mean value theorem is going to be one of the main things that we will be focusing on.